Okay. Okay. So, so let us recall that if if f is defined on an open set U of Rn to Rm, then we say that we say that f is differentiable at p belongs to U at p belongs to U uh, if components its components are differentiable at p. That is, if we write f as f of x1 x2 xn equals to, in terms of their component functions, so f1 x1 x2 xn, f2 x1 x2 xn, and so on, fm x1 x2 xn. Okay. So if you can write f x1 x2 xn as f1 f2 fm, these are the component functions of f. So if they have, then f is said to be differentiable at p if each fi's has continuous partial derivatives of all orders at p. Okay. And moreover, f is differentiable on u if it is differentiable at every point of u. Okay. Every point of u. Okay. Okay. And now also uh, let us recall that a tangent vector to a map alpha from an open set U subset of R to Rm at some point T0 belongs to U is defined to be the vector alpha dashed T naught equals to, so if you write alpha t as in terms of its components, so x1, x2, xm, then alpha dash t naught is, that is x1 dash t naught, x2 dash t naught, xm dash t naught. Okay. Okay. And note that it should be noted that for a given vector, suppose you consider one w belongs to Rm, for a given vector in Rm, and a point, suppose P belongs to U subset of Rm. Okay, one can easily define a differentiable curve alpha from where, from some interval minus epsilon epsilon to U, with the condition with alpha of 0 equals to P and alpha dash 0 equals to W. Say alpha can be defined as, it is P plus TW for all t belongs to minus epsilon, for all t belongs to minus epsilon open interval. Okay. So in this way, you can have for a given vector W and a point P belongs to U subset of Rn, one can easily define a differential curve alpha on U with the condition that alpha 0 is P and alpha dash 0 is W. That means it, the curve starts, the curve at 0 point, it represents the point P, and at this point you will have the tangent vector W. And in view of this, we can define the differential in this way, that suppose small a be a map from an open set U of Rn to Rm. So suppose it is a differentiable map, okay, to each point P belongs to U. So one can associate a linear transformation or linear map denoted by df at P from Rn to Rm. As we have seen that since f is differentiable, so you will definitely have, so it is differentiable at P, so you will definitely have a linear map from Rn to Rm in terms of the definition. Linear map this, which has been defined as the differential of the map F at the point P, and it will be viewed as like the following. So, what does it do in terms of geometry? That for a given vector, suppose W belongs to Rn, okay? For a given vector W belongs to Rn, and you have already considered one point P. So, with respect to this observation, you can define one curve, differentiable curve alpha. So, we can define a differentiable curve, right? Alpha from minus epsilon epsilon to u, so that at 0 it gives you P, and at the point P the tangent vector of uh, the curve at the point P is W. Okay, so that means, so therefore that is, this is your minus epsilon to epsilon, it is 0. So you are, suppose, say, suppose you are in R2 and you are going to, so it is a map from R2 to R3, for example. So this is your curve, so the curve, yeah, so this is your, suppose u, and this is your curve alpha, okay, and this is your P, and this is the tangent vector W. This is alpha naught, okay, and this is the W is the tangent vector of this. And this map, so if you impose this map F, then what does it differential do? So it will give you, for this alpha, it will give you one curve in R3, right? F compose alpha, which will be denoted by beta, right? And then at the point FP, this is your FP, the tangent vector to this point will be designated as, defined as DFP W. So this is the definition of DFP. Okay. So therefore, by using chain rule, you can say that the curve beta, what is that? This is alpha, F compose alpha from minus epsilon to epsilon to Rm. This is going to be a differentiable curve. Also a differentiable curve. Okay. Differentiable curve. And then we have DFP of W will be mapped to the tangent vector of this curve at the point FP. So that is, it is beta dash 0. Okay. Okay. So in this way, this differentiable will work from an open set U of Rn to Rm. Okay. So that means it maps tangent vectors, at the point P, to the tangent vector of this curve, at the point FP. Okay. So that means it maps tangent vectors at the point P, to the tangent vector of this curve, at the point FP. Okay. So that means it maps tangent vectors at the point P, to the tangent vector of this curve, at the point FP. Okay. two tangent vectors at the point FP. Okay, and note that this definition of DFP of this differential, it doesn't depend on the choice of the curve. Okay, which passes through P. With the tangent vector, W. It doesn't depend on the choice of this curve, this alpha. Why? Why it is so? Because in terms of our Jacobian, so actually uh, as because uh, let f of x1 x2 xn will be written as in terms of its component functions, that is f1 of x1 x2 xn, f2 of x1 x2 xn, fm of x1 x2 xn. Okay, for all x1 x2 xn belongs to U, subset of Rn, right? Okay, so fine. So then uh, since the map F is differentiable at P, it implies that its components have have continuous partial derivatives of all orders at P, right? And not only that, the the map DFP is, it has been defined as, what is that? So this is actually the Jacobian at P, right? That means it is the del f1 del x1 del f1 del x2 del f1 del xn, right? And so on. So it is del fm del x1 del fm del x2 del fm del xn, right? So it is an m cross n matrix, and this representation tells you that this DFP is actually independent of the choice of alpha, right? So this is actually independent of the choice of alpha. Okay. So this shows that DFP is actually a linear map, right? A linear map which will be represented as as uh, a M cross N matrix having entries del f I del x z, right, for all I equals to 1 to m, for all j equal to 1 to m. Okay, which implies that DFP does not depend on the choice of the curve, on the choice of the curves alpha, because it does not, the representation does not include any choice of curves, right, alpha. It only includes the partial derivatives of the component maps, okay, with respect to each variable. Okay, uh, this that I should mention in with respect to usual basis, yes, that I should mention, yes. Okay, and this is called the Jacobian of this map at P. Okay, so using this one, uh, so using this representation, so yeah, so our the inverse function theorem looks like the following in terms of this differential. So inverse function theorem. Let f colon u subset of Rn to Rm be a differentiable map and let E belongs to U. Okay, let P belongs to U, where where we suppose that the differential DAP from Rn to Rm is an isomorphism, linear isomorphism. Okay, that means it is 1 1. Then there exists a neighborhood V of P in U and a neighborhood W of FP in Rm. Oh, sorry, I do not take. Yeah, sorry, I should take Rn. FP in Rn such that such that small f from V to W has a differentiable inverse. Okay, differentiable inverse F inverse from W to V, which says that V and W are diffeomorphic, right? Are diffeomorphic, are diffeomorphic, having a diffeomorphic under F having differentiable inverse F inverse. Okay, from W to P. So this way you can state the inverse function theorem in this way. Okay. Okay. Now uh, now we would like to move to define surfaces in R3. What is the definition? A surface, what does it mean? Intuitively speaking, a surface is a subset of R3. So intuitively speaking, a surface is a subset of R3 that looks like a piece of plane. R2 around a point. Okay, around a point, and most likely, most likely, uh, uh, it uh, resemblance with the situation of of staying in the surface of the earth. Yes, in the surface of the earth, which is globally which is globally a sphere, but locally appears to be a flat plane, right? Appears to be a flat plane to an observer, on the surface. Yes. Okay, on the surface. If you if one sees the horizon, if you look at the horizon, then you will feel that you are living in a plane locally, but actually globally the surface represents a sphere, right? So that is the idea of the uh, concept of a surface in R3, and this idea will be reflected in the definition. What is the definition? The subset S of R3 is defined to be a surface, to be a surface if for every point P belongs to S, there exists an open set U in R2 and an open set W in R3, W in R3 containing that point, containing P. So there exists an open set U in R2 and an open set W in R3 containing P, such that curly S intersection W, that is the open set in S at P with respect to W, that will be homeomorphic to U. Okay. So this is the basic definition of a surface that is homeomorphic to U, which means that, so this means that a surface is actually is basically equipped with a collection of homeomorphisms, right? A collection of homeomorphisms sigma from U to S intersection W, which are called surface patches or parametrizations or coordinate charts or simply charts. Okay, and the collection of these homeomorphisms are called atlas. Okay, so the collection of these surface patches and the collection the the collection of all these surface patches is called the atlas of Callias. Right? It should be noted that each point of S will lie in the image of at least one surface patch, right? At least one surface patch in the atlas of S. Okay. Now, for basic example, what is the basic example? So, the first basic example will be a plane. A plane in R3 is a surface. A plane in R3 is an example of a surface. Which can be covered by a single surface patch. Okay, by a single surface patch. Okay. Why it is so? Because if you represent a plane in R3 passing through a point and parallel to some unit vectors P and Q, uh, which vectors are perpendicular to each other, is given by, suppose, uh, mm, so the equation of a plane passing through a point suppose P, and parallel to the unit vector vectors A, B, which are mutually perpendicular. Which are mutually perpendicular to each other is given by, so sigma of u comma v is P plus AU plus BV. Okay. So this is the representation. Okay, we should write it as 1 minute. This will be UA plus VV, since A and B are vectors. Yeah. Okay. Yeah. So then, this will be your surface patch, which covers the whole plane, having so sigma UV is the surface patch which covers the whole plane whole plane with its inverse. What is the inverse? So with its inverse, sigma inverse of the points r from the plane will be represented as, so this is your r minus p a, r minus p b. Okay, which is continuous, right? Which is continuous. That implies that uh, sigma is a surface patch. Hello. Okay. For example 2, uh, if we recall that the mm, stereographic projection uh, of S2 and the extended complex plane, then we see that we see that uh, then we see that R2 uh, then we see that, yes, the homeomorphisms the homeomorphisms sigma from S2 minus north pole to R2 and psi colon S2 minus south pole to R2 will constitute the atlas of S2, right? That is uh, sigma psi are surface patches of surface patches with respect to which we can cover S2, right? So in this way we will have surface patches, so therefore S2 represents a surface. Okay, so S2 represents a surface, and also if we consider if we consider uh, another two maps sigma phi theta comma phi equals to cos theta cos phi cos theta sin phi sin theta minus pi by 2 less than theta less than pi by 2, and phi will be varied from 0 to pi. Okay, whatever. And psi colon theta phi equals to minus cos theta cos phi minus sin theta minus cos theta sin phi these two maps. So this is from again minus pi by 2 less than theta pi by 2 and 0 less than pi less than 2 pi. So our two
রানাদা মিউট করো, একটু সাউন্ড আসছে।
are two surface patches
করে দেন।
of the sphere. Okay, which covers S2. Okay, so that means if you look at these two maps, sigma and phi, you will see that observe that psi is obtained by first rotating sigma by an angle pi about z axis, and then by pi by 2 about x axis. Okay, also we see that if we let u equal to theta comma phi, where minus pi by 2 less than theta less than pi by 2 and 0 less than phi less than 2 pi. So this is an open set in R2. Then you will see that sigma u is not the whole sphere, right? But rather, uh, we can say that sigma u, yes, sigma u is the complement of uh, of some great circle. Yes, great circle, which is C. C is x comma 0, so x 0 z, where x greater equal to 0. Okay. So for that reason, you need to define another surface patch psi to cover the part of the sphere omitted by sigma, right? So this uh, this says that we need to define another surface patch psi to cover the part of the sphere which has been omitted by sigma, right? And also note that the image of psi is actually is also uh, is also the complement of the great circle actually. I'm sorry, maybe semicircle, I think. Yeah, yeah, sorry, great semicircle. Yes, I don't write it as circle. Great semicircle, the part of the circle, great semicircle, C dashed, consisting of the points x, y 0 with x less or equal to 0. Okay. Okay. And to be more precise, we see that sigma is a homeomorphism from from u, yes, we have defined u, this one, u onto S2 intersection W, where what is W? Is x, y, z belongs to R3, where x less than 0 uh, or y not equal to 0. Yeah, yeah, okay, fine. So, yes, so in this way you can say that, so this produces another atlas of the surface S2. Okay, fine. Okay.